Yep.
Yeah. So Kong, you can, you want to do the second one, or first? What do you want?
Whatever you prefer.
Well,
I don't care.
I can do both of them. I'll start it. Okay.
All right. Yeah.
So are you still using your EIK?
Yeah,
It's run okay for you?
yeah. We just, yeah, I mean, it's been very good. The one time it got damaged was just in shipping it back.
Yeah.
The CPI that got dropped, they dropped it off the truck and
Mhm.
it got damaged, and then we had to kind of replace it. But otherwise, it's been pretty reliable. We've had a little trouble actually with the chiller unit for it. So we just replaced the chiller, which is from Thermo. And now things are working smoothly again, I think.
Mhm.
But the chiller was acting weird, and that was causing the power supply to shut off because there's all kinds of interlocks and things like that. So there was just some problems with the chiller, it turned out, not the EIO itself. But
Mhm.
basically it's been good. Yeah. Ours is like 1.5 watts. I guess the ones that Brooker, Brooker sells with its DNP are higher power.
There's supposedly 5.
Yeah, so those, I don't know
They go- I mean, they've just improved. Kurt Zim wants to know why he can't see the list of attendees.
why does he need that?
Kurt, you have to ask Kong about that. He's in charge of that part.
Because that's the
Distinguished
problem.
list, I can see it.
Yeah.
There's some good people there. I better give a good talk. Uh-oh, now the pressure's on.
Yeah. Yeah, they actually dropped Claire Gray's too. So, I mean, there was a transit problem, yeah. And it had to go back to,
Canada.
yeah, and then it spring a leak, apparently.
Ours has been good.
I mean, that's a common failure mode in these devices, is that they're all water cooled. And the collectors typically, they make them, you're always cramped for space and the walls get thin, so there's corrosion. And we've had 2 gyrotron tubes fail because of water leaks in the collector.
Yeah, that hasn't happened in ours, but it's a concern.
Uh-huh. Mhm. So, okay. All right, so why don't we get going? It's 10:05 almost, within a few seconds. All right, so today we have 2 excellent talks, 2 excellent speakers for the presentations. Rob Tycko, who is from NIDDK, and he's going to be telling us about imaging with DNP, imaging of microscopic small structures with DNP. And the second talk is by Rob Schurko, who is from the National High Magnetic Field Lab, and he will be telling us about excitation, acquisition, and so forth of spectra of a very, very wide line NMR spectrum. Now, Rob Tycko, our first speaker, was an undergraduate at Princeton University. He was then a PhD student with Alex Pines at Berkeley, where he worked on pulse. I've forgotten what the pulses you developed were called, but they were very exotic excitation pulses, among other things. He was in a postdoc with Stan Opella at the University of Pennsylvania before Stan moved to San Diego. And then he moved from there to, I think, Bell Telephone, what was known as Bell Telephone Labs or Bell Labs for a few years, and subsequently to NIH, where he's been for the last 20 or so odd years. And Rob has done a very, very large number of very important things. Among other things, he's worked out a lot of structures and models and so forth of A beta, Alzheimer's protein, and he's also been involved in the development of new methods for magnetic resonance. And that's what he's going to tell us about today, are his new experiments. He claims to be a world record imaging, 1.3 micron resolution that he's done with dynamic nuclear polarization. So Rob, the virtual floor is yours.
Thank you very much. It's a pleasure to be here. And thank you, oops, I didn't want to, it's the wrong screen. Thank you, Bob and Kong, for organizing this very valuable series of online seminars. What's going on now? You see my slide now?
Yes.
It's working? Okay.
Yeah.
Very good. No, this series has really been good during the pandemic era in terms of keeping us motivated and keeping us connected. So thanks very much for your efforts. Okay, today I'm going to talk about one of the projects that's been going on in my lab for some time now, for more than a decade, where we're trying to push the spatial resolution limits of magnetic resonance imaging by going to low temperatures and using DNP. And people who have contributed to this project, I hope you can see my cursor. Ken Thurber did some experiments at the very beginning to get it started. I'll show you those. Ming Yao has synthesized nitroxide-based triradical dopants that we use for DNP in our experiments. Eric Moore, who now works for Brooker, was the first postdoc in my lab who worked on this project. And then Suing Chen, who recently started working for Brooker, also did the more recent experiments, and I'll be showing you his results. And this is the world's record that is described in the title, mentioned in the title, 1.7 microns, not 1.3. We're working towards 1.3. 1.7 micron isotropic resolution magnetic resonance image obtained at around 5 Kelvin with DNP. It's just an image of small glass spheres inside of a capillary tube that's filled with glycerol water. So it's not intrinsically interesting, but it demonstrates the potential of this approach, I think. And it's by far a world's record, as you'll see. Okay, how did this get started? So a little bit of the background. So we started doing DNP about 12, 13 years ago after Bob Griffin convinced me it was a good thing to do. After his lab started getting all kinds of very promising and exciting results, we decided we would give it a try. But I wanted to start sort of gradually. So we started off with a very low power microwave source, 30 milliwatts from Virginia diodes, quasi-optic system for polarizing the microwaves from Thomas Keating. And the initial experiments were done without magic angle spinning, just static experiments. I wanted to get some sense for how DNP worked and what kind of enhancements we could get. And these were experiments done by Kent using this triradical dopant that Ming developed, which turns out to have some advantages. I think it gives you somewhat faster buildup of polarization compared to biradicals, I think mainly just because more of the radicals actually participate in the DNP process when you have 3 unpaired spins in each radical rather than 2. For the cross effect DNP mechanism. And these are just some of the results. So as you go down in temperature, so we did these experiments with the cryostat. You'll see more pictures of the cryostat later, but it's a cryostat that allows us to do experiments over a broad range of temperatures from 3 or 4 Kelvin up to room temperature, or maybe even higher. And so we could measure the enhancements as a function of temperature. And as you go down in temperature, the signals go up, signal to noise goes up. And you get a big advantage in terms of sensitivity, even taking into account the longer buildup times that you typically have at low temperatures. And so then I started thinking, well, what can we do with these very large signals, these large polarizations? And one thing that occurred to me was magnetic resonance imaging. Now, in magnetic resonance imaging, of course, it's a very widely used, very valuable technique for anatomical studies, for functional, cognitive processes, with functional magnetic resonance imaging, many other things, experiments on humans, experiments on animals. Since the very beginning of MRI, there's been efforts in various labs, efforts to try to push the resolution of MRI to the point where you could actually do MRI on cells. So that MRI could become a tool in cell biology to see structures inside of cells or arrangements of clusters of cells, things like that. And it's a long history of that. And I just listed some of the papers just so you can see some of the names of people who are involved in that. And the best that's been done just in terms of raw resolution is, first of all, around 2002, Charles Pennington's lab at the physics department at Ohio State University, they had a project to try to get to sort of micron scale MRI, and they eventually achieved resolution of about 3.5 microns isotropic roughly. And this is from their paper published in 2002, just showing an image of proton MRI image of polymer beads in copper doped water. So the water is what they're observing. Obtained at 9 Tesla, took them 30 hours to acquire the data here. So that's about 3.5 micron isotropic approximately. And then a little bit later in 2008, a group from Brooker pushed the resolution a little bit further at room temperature to about 3.0 microns at higher field, 18.8 Tesla. I guess that's an 800 megahertz magnet. Again, copper doped water. In this case, they had glass fibers in the water. They used this kind of a surface coil. And you can see the glass fibers are these dark lines, and the surrounding bright material is the copper doped water. And they got this image with 3.0 micron isotropic, they say, in 58 hours. So that gives you an idea of what the state of the art has been. And that's about as good as you can do at room temperature. And this is an example from my own lab that we never published, but a little bit more complicated. This is a C. elegans worm, a fixed formaldehyde fixed worm inside of a capillary tube. And this is obtained at 750 megahertz proton NMR frequency, 4.0 micron isotropic resolution. It took 40 hours to get this image, and you can actually see some stuff. These are the developing eggs or embryos within the worm. You can see those are the dark regions. In this case, the water was, again, paramagnetically doped with copper. The doped water doesn't get into the embryos or into the eggs, so they appear dark. But again, this is about as good as you can do at room temperature. And the reason for that is basically just the inherent signal to noise limits of NMR. And there's a nice discussion of that in Abragam's classic textbook in chapter 3, section 4B that I encourage you to look at. It's actually very thought-provoking when you read it and think about why, how things actually work. But Abraham derives an estimate of what the signal to noise of NMR is inherently. And of course, in NMR, the signal is a voltage this is inductive. I'm talking about just inductively detected magnetic resonance and magnetic resonance imaging, not force detected, but just inductively detected. The signal to noise, the signal is just the voltage across a solenoidal coil around your sample induced by the precessing nuclear magnetization. And the coil is part of a tuned circuit, an LC circuit. So there's a Q associated with that. So the voltage is, the signal voltage is amplified by the Q. And then the noise is just the noise due to random thermal currents in the coil and the resistance in the coil. So it's the ratio of those two things, which Abraham calculates in the sort of most ideal case for a perfect solenoid. And you get an expression that looks like this, various constants. And then for proton NMR at 400 megahertz, if you express things in terms of the molar concentration C of the spins, protons inside your sample, assuming that your sample fills the coil has a volume V in milliliters. There's a line width W in hertz, and everything is at temperature T. So the sample and the coil itself, the circuit is at temperature T. And we're assuming that there's a Q of 100, then you get this number. It's about 3 times 10 to the 9th times these factors. And then for magnetic resonance imaging, there's also a filling factor, because to get an MRI image where the individual volume elements or voxels have a certain size, so for a certain voxel volume, you have to be able to detect the signals from the individual voxels. So if you want to get 1 micron, obviously, if you want to get a 1 micron resolution MRI image, you have to be able to detect the signals from 1 cubic micron of material. And then there's a filling factor, which is the ratio of that voxel volume to the total coil volume, V. Okay. So then you get this expression, but this, obviously, this filling factor is very small typically. Might be on the order of several thousand or something, 1 over several thousand. So that reduces things further because you're just detecting an individual volume element within a larger coil. So if you then plug in some numbers for typical NMR experiments, you have 100 microliter or something coil volume. If you're detecting proton NMR signals from water, if you want to get 10 micron isotropic resolution with a signal to noise ratio of 10, in principle, you could get that in 100,000 scans, about 28 hours, about a day with 1 scan per second. If you wanted to go to 3 micron resolution, then the filling factor would be much smaller. And it would take 10 to the 8th scans, would be impossible basically to do this experiment. So this is why micron scale MRI is so difficult. It's just the inherent signal to noise limitations of NMR. So the only solution to get to high resolution at low temperatures is to use a very small coil. So typically you use a micro coil that instead of having a volume of 100 microliters, maybe has a volume of 5 or 10 nanoliters. And then if you look at this expression, you're reducing the total coil volume, but you know, there's a square root of V factor here, but then this filling factor or the volume fraction per voxel increases as 1 over V. So overall, the time scales as 1 over the coil volume, the time it takes to acquire the image in principle. So you get a big gain by going to a very small coil. And then you also have to do paramagnetic doping, so you can pulse faster than once per second. And then typically you use things like car per cell echo trains, or in our experiments, pulse spin locking, to try to extend the signal per scan as long as possible, get as much signal, integrated signal per scan as you can. But the best you can do at room temperature is about 3 microns isotropic in practice. Can we do better by going to low temperatures? Because there's also this 1 over T to the 3/2 factor in principle. And then also at low temperatures, in addition, you can use DNP, for example, cross effect DNP, and that can gain you an additional factor of 100 or something here. So it seems like there's a chance that you could do better by going to low temperatures and using DNP. Of course, if you go to low temperatures, then your sample becomes a solid, and then now you're doing solid state imaging instead of liquid state imaging. So you have to worry about the line widths, the magnetic dipole-dipole couplings among the protons if you're doing proton NMR, proton magnetic resonance imaging. So you need to apply some kind of homonuclear decoupling method in order to narrow the lines. And even then, you probably can't make them as narrow as you can at liquid at room temperature. So there's issues with going with looking at a solid. So does that work? So initially we did some experiments, or Kent did some experiments published in 2010, just to test whether this idea makes any sense. What's the possibility of getting to microns or maybe sub-micron resolution by going to low temperatures and doing solid state MRI with DNP, with the same DNP system that I just showed you a couple of slides ago. And in these experiments, Kent used Lee Goldberg homonuclear decoupling, just giving a strong RF field, far off resonance. So the effective field in the rotating frame is at the magic angle with respect to the z-axis. That is the original method for homonuclear decoupling, and it actually works very well with microcoils because you can apply very strong RF fields. So typically we use RF fields of on the order of 200 kilohertz, 250 kilohertz for Lee Goldberg decoupling. So that's what we used here. It's actually phase switched Lee Goldberg only because by switching the direction of the Lee Goldberg field in the middle of one of these periods, you cancel out effects of RF inhomogeneity, really. So that refocuses RF inhomogeneity effects here. But basically, he was using Lee Goldberg decoupling during the imaging period. In this case, he wasn't actually applying gradients for imaging. He was just giving a DC field pulse because our cryostat at that point had a field modulation coil in it that allowed him to apply DC field pulses, and then detecting with pulsed spin locking, detecting the signals in intervals between spin locking pulses to extend the FID as long as possible, get as much signal per scan. And these are just some of the data that he got, just showing that actually it is in principle feasible. So the conclusion of this paper was that sub-micron solid state NMR imaging at low temperatures with DNP is a reasonable goal from the sensitivity standpoint. There's a chance that it might actually work. And so based on the results in this paper, we decided to pursue it. And the first experiments were done by Eric Moore when he was a postdoc in my lab, and Eric designed the MRI apparatus, the design that we've actually been using since then, which is a design where the gradient coils and the RF microcoil are mounted on sapphire plates that are stacked on top of one another. And by mounting the coils on sapphire plates, you accomplish two things. First of all, sapphire has high thermal conductivity, especially at low temperatures, so you can dissipate the heat in the gradient coils when you give large pulses, and we give pulses up to about 80 amps in the experiments that I'll describe to create adequate gradients. And so you need to dissipate the heat in those in the microcoils in the gradient coils. And so by mounting them to sapphire, gluing them in place with die-cast epoxy to sapphire plates, you can dissipate the heat. You can also make sure that your sample is actually at the temperature that you want it to be at, because the sample is also thermally anchored to these sapphire plates. And then also by having a stack of them, you can disassemble the MRI apparatus by just loosening a few screws, and then you can unstack the various components, and that allows you to change samples and things like that. So that was the design. Turns out with this design, as Eric showed, you can get sufficiently strong magnetic field gradients in X, Y, and Z directions on the order of 0.4 Tesla per meter amp, which translates into about 17 Hertz per micron per amp. So if you apply a 100 amp current pulse, that gives you 1.7 kilohertz per micron. So if you have sub kilohertz line widths, then you can actually separate them so you can get adequate spatial resolution. So the gradients are actually not the limiting factor. It's really the signal to noise. And this design also allows microwaves to pass through holes in the sapphire plates to reach your sample. And I think I'll show you a picture of that later. So with this apparatus, Eric did some initial experiments at just that room temperature imaging of ammonium chloride particles. So this was solid state imaging using the same kind of pulse sequence that I talked about before, and got room temperature, about 8 micron isotropic resolution for these ammonium chloride particles, which again, for inductively detected solid state imaging was also a world record for solids. I already mentioned those things. And then Suing Chen joined the group as a postdoc and took over this project and did low temperature experiments, initially without DNP at 28 Kelvin, using the same device, essentially with some minor modifications, and obtained an image of glass beads with a 20 micron diameter inside of a 75 micron inner diameter capillary tube. And these are some of the slices from that image, just showing that you can easily see the beads with reasonably good contrast. And the resolution of this image was 2.8 microns. And this was obtained at 28 Kelvin in about 200 hours. So a very long experiment, but 2.8 microns is a little bit better than the 3.0 micron isotropic resolution that had been obtained previously by the Brooker group at room temperature. So this just demonstrates that, in fact, you can do low temperature solid state MRI with very similar resolution to what you can achieve at room temperature in liquids. This is without DNP. So now you figure if we can just get a factor of 50 signal enhancement from DNP, to the resolution, I'm talking about the resolution in each of 3 dimensions. So a factor of 50 signal enhancement allows you to reduce the voxel volume in principle by a factor of 50. That gives you a cube root of 50 or factor of 3.7 improvement in each individual dimension, all other things being equal. So just by applying DNP, if all other things were equal, we should be able to get to below 1 micron resolution. Now in practice, though, not all things are equal. So when you go from a non-DNP to a DNP situation, in the non-DNP situation, we were using dysprosium doped glycerol water, which allowed Suing to pulse rapidly. I think the repetition rate was about, I think it says 0.4 second recycle delay, so 400 millisecond delay between scans. You can do that by dysprosium doping with DNP. The buildup time is much longer than that. But on top of that, there's problems with paramagnetic relaxation effects when you add DNP dopants to your samples. So the DNP dopants that we use are these nitroxide tri-radical compounds, and they're typically used at relatively high concentrations. And so at the temperatures we were working at in Suing's experiments at around 30 Kelvin, you have flip-flop transitions involving the electron spins on individual molecules and also between the molecules because the concentrations are relatively high. And these electron spin flip-flop transitions give you fluctuating local magnetic fields, relatively slowly fluctuating magnetic fields, sort of micron timescale, that give you rapid dephasing of the NMR signals, both during the imaging period, the so-called phase encoding period, we're applying the Lee-Goldberg irradiation, and then also during the pulse spin lock period. So you can compare the signal decays as a function of the Lee-Goldberg decoupling period, and it's a function of the spin locking period for a DNP doped sample versus a dysprosium doped sample, and those decays are much faster in the DNP case. So that signal losses due to signal decay from these paramagnetic relaxation effects largely cancel out any gains that you get from DNP. So that's a problem. But then if you look at the temperature dependence of the electron spin polarization, you see that at a 9.4 Tesla magnetic field, 400 megahertz NMR frequency, the electron spin flip energy is on the order of 11 K. So that means that when you get below 11 Kelvin, the electrons start to become very strongly polarized, where they're at thermal equilibrium, they're primarily in their spin up state. If the electron spins are fully polarized, so all the electrons are pointing in the same direction, then you can no longer have flip-flop transitions. So then the relaxation times, these transverse relaxation times that I'm plotting here should become much longer. And then Suing demonstrated that that's in fact true. If you look at the temperature dependence of these decay times, signal decay times, you find that when you get below 10 Kelvin, the decay times start to go up again. So by going to very low temperatures, you can overcome these, largely overcome these relaxation effects. There's still a problem that the DNP buildup time is slow. And what that means in the experiments I'm going to show you now is that we can't use the full DNP enhanced polarization. We're only using buildup times on the order of 2 seconds. So we're only using a small fraction of the available polarization because we still need to acquire many scans just to reconstruct an image. So typically, if you have an image with 25 to 50 points in each dimension, you need to take something like 100,000 scans just to acquire all the data you need to reconstruct that image. And even with 2 seconds per scan, it takes 50 hours to do that. If we actually use the full DNP polarization, it would take much too long to do the experiment. All right, so given all those constraints, though, Suing in the past year before leaving my lab last spring obtained the data for the image shown here. So this is the image that I showed at the very beginning, 1.7 micron nominal isotropic resolution. The nominal resolution is just determined by the maximum gradients that you apply. Just like in NMR spectroscopy, the resolution is determined by the maximum length of your T1 or T2 periods. In a time domain multi-dimensional experiment. In this case, it's actually a 4-dimensional experiment. We're doing all the imaging in indirect dimensions. We have 3 indirect dimensions that are actually happening simultaneously. And the resolution, the spatial resolution is just determined by the maximum gradient that we apply. So the nominal resolution based on gradient strengths is 1.7 microns. And this is an image of spheres that are 9.2 micron diameter. They're immersed in glycerol water. The glycerol water is only 10% protonated, so we get a more rapid DNP buildup that way, doped with 10 millimolar of this triradical dopant. Sample temperature is 5 K. Signal to noise, you can see here, is on the order of 15. So these are slices in different directions. The beads are inside of a capillary. So basically the image looks pretty good. Is the resolution really what we claim it is? Is it really 1.7 microns? So we assess that in 2 different ways. One way is to actually make a simulated image of spheres inside of glycerol water. Spheres are dark, the glycerol water is white. And then we just broaden the spheres out. We apply sort of a Gaussian line broadening or Gaussian blurring or a Gaussian point spread function to the image. And then we compare this broadened simulated image to the experimental image, and we optimize the position of the spheres, and we calculate the square deviation between experimental and simulated images, and you get these kinds of curves. We do that at various positions within the experimental image, and you see the minimum square deviation is around 1.7 microns typically. So this is one piece of evidence that we actually are getting an image with 1.7 micron true resolution. Now, our real experiments, our real images don't really have a Gaussian point spread function. In our real images, we're acquiring K-space data. It's like time domain data in the case of spectroscopy, but for imaging, it's the K-space data. It's the data as a function of the gradient strengths, which are incremented in the indirect imaging dimensions. We're acquiring the K-space data out to a particular maximum value, K max, to get the desired resolution. And then we're zero filling those data and Fourier transforming them. And so what you get, the point spread function that you get from that is some more complicated thing, like a sinc function with wiggles on it and everything. I'll show you an example of that in a second. So another way of verifying the spatial resolution is actually to simulate the actual K-space data, truncate it at the maximum value of K that you use in the real experiments, and then Fourier transform it and compare it to the images. And these are plots of that where we've actually plotted it's a little bit complicated, in 2D planes, either in the X direction, which is the direction along the capillary axis in our experiments, or in the z direction, which is one of the directions perpendicular. We calculate the k-space data in two-dimensional planes perpendicular to x or y. And we do that for the experimental data, which is in blue, and for simulated images in red. And we find that the k-space, simulated k-space power matches the experimental k-space power out to the point where the noise becomes a significant contribution. At that point, the experimental k-space power is higher because it's the sum of the signal and the noise power. But again, the good agreement here supports the idea that our image resolution actually matches the nominal resolution. Okay, now one funny thing that we find if you look at these images, both the experimental and these simulated images, is that there's a bright spot in the middle of each of the dark spheres. And that puzzled us. If you could look at these experimental images carefully, you can see bright spots in the middle of each of the dark spheres. And that, when we first saw that, and when we processed the experimental images, this was a surprise. Why is there, these are supposed to be solid glass spheres. Why is there like a little pocket of water inside of each sphere or something? Why do we have these bright spots? Well, that turns out to be really a result of this k-space truncation, or the point spread function that I was just talking about. Depending on where you truncate your data, if you actually truncate your data at k-space corresponding, maximum k-space corresponding to k-value corresponding to 1.7 micron resolution, then you actually expect to see a bright spot in the middle of each sphere. And that's because of these sort of truncation wiggle artifacts that you can simulate as shown here. So the fact that we see these bright spots in the middle of each of the dark spheres is another sort of qualitative support for the idea that we actually have the resolution that we expect. All right, so I'm really done showing you the results. I just want to quickly, I'll just flip through some of the experimental details, and then you can ask me questions if you want. So here's our the apparatus, the microwave apparatus that we're using for these experiments that Suing used. It's actually, we actually have two VDI sources, one original source that was around 30 milliwatts, a source that we got later that's a little bit higher, maybe 50 milliwatts, but the second source, we can actually rapidly rapidly modulate the microwave frequency over, and we modulate it over about a 0.3 gigahertz range, around 263 gigahertz, which is the optimal frequency for DNP, cross-effect DNP in our magnet, sweeping back and forth at a 2 kilohertz rate. And Suing optimized the center frequencies of the two sources, optimized the sweep range, all that stuff. Also optimized the orientation of the cryostat inside the magnet, because the microwaves have to penetrate through a solenoid coil. And so depending on the polarization of the microwaves, there may be a particular orientation of the cryostat that gives you better microwave penetration. So all those things were optimized. Cryostat is a type of cryostat that we've used in many experiments in my lab over more than 30 years, really. It's a variable temperature, cold finger in vacuum type cryostat, where it's basically a vacuum can that has a window at the bottom. I guess we can't see the window here, but we have a Teflon window at the bottom that allows microwaves to come in. Inside of the cryostat, the cryostat can is evacuated. There's a radiation shield around the sample area that contains the MRI apparatus that I described before. There's a microwave horn that's mounted on the radiation shield. So microwaves come from outside the cryostat through a Teflon window. They enter this horn. They're carried through the horn. And then at the end of the horn, I guess it's not shown here, there's a little tapered Teflon waveguide essentially that carries the microwaves into the hole in the top, in the hole in the sapphire plates that allows the microwaves to enter. This is the solenoid coil viewed down through the hole in the top of those sapphire plates. So you can see there's a solenoid coil that's wrapped around a 100 micron capillary tube. This is just showing what happens when you disassemble. By unstacking those sapphire plates, you can expose the various gradient coils. This is our gradient design for the X and Y gradients. So there's a pair of coils with the currents flowing in the directions shown here, which produces a gradient between the two center wires here. The Z gradients are a pair of circular coils with the currents running in opposite directions. And as I said before, this gives us about 0.4 Tesla per meter amp gradients. Some of the details of the pulse sequence. So one interesting thing is that the DNP buildup time, polarization buildup time, depends on how the microwaves are configured. So if you optimize the microwaves so that you're getting the maximum possible signals, that means you're using the maximum number of DNP dopants, the maximum fraction of DNP dopants in your sample dopant molecules are contributing to the cross effect DNP effect. So then you also get the most rapid buildup. So we're getting a buildup time of about 6 seconds. This is in 10% protonated glycerol water. This is how the signals decay as a function of the Lee-Goldberg period during which the gradients are applied. And you can see here that the resolution is the product of the maximum gradient with the length of that Lee-Goldberg period. And in principle, we could make that resolution better by just using a longer Lee-Goldberg period, but then we lose a lot of signal. So there's a very direct trade-off between resolution and signal to noise in these experiments. And so we've used a Lee-Goldberg period on the order of 0.7 milliseconds. Some of the other details. So the Lee-Goldberg decoupling, as you know, depends on applying a strong effective field at the magic angle with respect to the Z-axis in the rotating frame. And when you're doing imaging, you're applying strong gradients, and the strong gradients produce large additional offsets from the NMR frequency depending on the position. So there's a strong, if you're far away from the center of the gradients, there's a large additional offset that either adds or subtracts to your Lee-Goldberg offset that you've deliberately introduced. So that means that the direction of the effective field depends on the position within the sample. And if you're applying strong gradients, that's a significant effect. So then consequently, it's not good to have the gradients on when you first turn on the Lee-Goldberg field or when you switch from the positive Lee-Goldberg field direction to the negative field direction, which means switching the phase of the RF and switching the direction of the Lee-Goldberg offset. Because you want in this pulse sequence, we want the magnetization to be perpendicular to the effective field direction so that we get precession around the Lee-Goldberg effective field during the imaging periods, during the phase encoding periods. So if the direction of the field is variable, then you can't guarantee that your magnetization is perpendicular to that direction. So it's good not to have the Lee-Goldberg fields on when you first prepare your transverse magnetization. It's not good to have them on when you switch your gradients, or it's not good to have the gradients on when you're switching the direction of the Lee-Goldberg field, because that gives you these strong spin locking effects. You get strong magnetization components that are spin locked to the effective field, and that gives you big artifacts in the data. So we turn the gradients on and off gradually, and we turn them off when we switch from one Lee-Goldberg direction to the others. So that reduces artifacts, because then the precessing fields can adiabatically follow the effective field direction as the gradients are turned on. So that's kind of a subtle effect. We do a slice selection to limit the field of view. I don't have time to talk about that. I'm going to just show one last slide because I've used up all my time. So we've reached about 1.7 micron resolution. We would like to get to 1 micron or better. So we need another factor of 5 improvement in signal to noise ratio to get to 1 micron or better. So how can we get that? Well, there's some straightforward ways of doing that. One thing is that in the experiments shown here, in Suing's experiments, where we got the 1.7 micron isotropic resolution, we're using just a standard preamp in our receiver, standard room temperature preamp, a pretty good preamp with a noise figure around 1 dB. But that means the noise temperature of the receiver is around 80 Kelvin, but our sample temperature is 5 Kelvin, which means that most of the noise is actually not coming from the sample. or from the coil around the sample. Instead, most of the noise is actually coming from the preamp. So we should really use a cooled preamp, a cryogenic preamp, to reduce the noise temperature of the receiver, and that could give us a factor of 4 improvement in signal to noise. So already, just by using a better preamp, we're almost where we need to be. A fully protonated sample rather than 10% with a more efficient DNP polarizing agent that gives faster buildup could give us another factor of 10. So there's a lot of room for improvement in DNP polarizing agents to give us faster buildup. Even lower temperatures, so we're working at 5 Kelvin, we could go to pumped helium and then get down below 3 Kelvin. This would further reduce the nuclear spin relaxation driven by electron-electron flip-flaps. That could give us another factor of 2. In principle, we can use non-uniform sampling to get another factor of approximately 2 by reducing the required number of K-space points, basically not taking all of the K-space points and then using some other image or data analysis rather than a Fourier transform to get the image. This would allow us, by reducing the number of points that we're taking, we could use larger values of the DNP polarization time, get more signal per scan, and that could give us another factor of 2. So I think we can get there in the relatively near future. And then the question is, what are the applications? And you're probably wondering about that already. And the answer is we don't know yet. It depends on how well everything works. So right now, so far, this has mainly been a technological exercise. But once we get to 1 micron or better resolution, then we're getting to the point where we're really competitive with optical imaging, maybe with super resolution optical imaging. And then we can start thinking seriously about applications where we can get information in this way that's not otherwise available. Thanks very much for your attention. Thanks to these people for contributing to the work. If you have any questions, I'll try to answer them.
Okay. Thank you, Rob, for a really nice talk. And there are 4 questions, at least in the Q&A already. And if you have more questions, please submit them to the Q&A. So Thomas Schmidt wants to know that is true that it would be polarized lower temperatures, but would also be dependent on the magnetic field you record at. Is that correct? And if so, then recording imaging at lower magnetic field would be preferred.
So if the question is there really an advantage to being at the field we're at? I'm not sure. If you can get better, I mean, by going to lower fields, you're inherently losing signal to noise. But if you can gain that back by more efficient DNP, then it's better to go to lower fields. I mean, in this case, our resolution is, we're talking about spatial resolution, so it has nothing to do with spectral resolution, really. So lower fields could be better, but we're not planning to go to higher fields with these experiments, put it that way.
And Jeff Reimer says exciting images. Were the latest data also obtained with the LG decoupling and spin lock detection? Any subtitles about how you do that? He says, oh, you've just answered that. You've answered a lot of it, probably. Maybe there's something else you want to add? Huh?
I mean, this is the pulse sequence that we used. I described some of the tricks. The one thing I didn't talk about was the slice selection. So, you know, as I said before, you know, we want to limit the number of volume elements within our image. We can't have too large an object that we're imaging, because then we just need to take more K-space points. And that means we can't, you know, we have to make the DNP buildup time even shorter, which means less signal per scan. So that we want to limit the part of the object that we're actually imaging. And so we do this with the slice selection technique. That's one thing I didn't talk about. It's a simple slice selection technique that selects out signals within a particular frequency range just by giving pi pulses in the presence of a strong gradient along the x direction. So that then limits the imaged area in the x direction as shown here, and completely suppresses the background signals. So that's one little trick that I didn't talk about. I think I probably talked about everything else you need to know.
Okay, and so Lucio says, great talk, Rob. Great stuff, Rob. 2 questions. Why the tri-radical? Did you try other polarizing radicals, polarizing agents? And 2, besides signal to noise ratio, resolution in regular MRI is limited by diffusion. Once residual spin diffusion you have in the FSLG have a similar blurring effect.
Well, I mean, spin diffusion is much slower. Spin diffusion is on the proton-proton and fully protonated material. Spin diffusion is on the order of, 10 nanometers in a millisecond, something like that. So it's as opposed, so it's really spin diffusion. I think we're not at that point yet. I hope we get to that point, but we're not at the point where spin diffusion is actually giving us a broadening. But I mean, in a way, that's one of the advantages of looking at low temperatures. You don't have the translational diffusion, which otherwise can be a limitation.
So what about the tri-radical? He asked you about.
Okay, and about the tri-radical, I mean, in our hands, the tri-radicals compared to biradicals give us faster buildup for the same total electron spin concentration, just because, for the cross effect mechanism, you have to have a pair of nitroxides that are kind of at the right orientations relative to one another. And that means only some fraction of the molecules can contribute. If you have 3 of them instead of 2 of them, it's more likely that at least there's going to be 1 pair out of those 3 that is able to participate. So that's the rough hand waving explanation. So we use the tri-radicals because we get more rapid buildup. But maybe there's something better. As I said, that is, we want something that gives us, the most polarization in the shortest possible time. So we're open to suggestions.
Yeah, I mean, the biradical structures that you have about 20 megahertz couplings. I'm not sure what the biradicals. Okay, now I don't know. I mean, you could look at the tri-radical couplings in the EPR, and for Amupol, the radical that came out of Marseille has about a 35 megahertz coupling. It's,
I mean, Amupol definitely is slower buildup. We've used Amupol not in these experiments, but in our magic angle spinning experiments at 25 Kelvin. It's like a factor of 2 or something longer buildup time in our hands at these low temperatures for the same total electron spin.
Well, I would have said maybe trying to make the coupling larger, but anyway, okay.
Yeah, I mean, at very low temperatures, I think my understanding is we're limited by the electrons T1.
Yeah.
So we want radicals with shorter T1s, and then so there's these tricks of adding other metal ions to try to reduce the T1s. We need to investigate that more thoroughly. Suing did some quick experiments that seem to suggest it didn't help us, but we need to re-examine that.
Yeah,
maybe that'll help.
So Aaron Rossini says, I'm amazed how long the proton T2 is under pulse spin locking. It looks like you routinely achieve a T2 prime between 20 to 100 milliseconds. Is that typical for protonated solids like frozen water, or where your samples partially do
it? It is, yeah. No, that is also one reason for using the 10% protonated. So it's 10% protonated glycerol water.
And so presumably there's significant contribution of stimulated echo pathways to the PSLFIDs as well, which would help to extend the apparent T2.
That could be. The pulse spin locking, I've just been treating it as an empirical fact that it works. But I think, there are papers written about why it works, and it's maybe not so clear and exactly what the optimal, just empirically optimize the flip angle of the individual pulse spin locking pulses. I'm not sure I don't know if there's a predictive theory of it yet. Maybe there is.
Okay, and Mark Conradi says, did you use K-space symmetry of half Fourier to reduce the number of K values?
We took, we could have, Suing took both the positive and negative K points everywhere. You don't have to do that. You just have to take really 1/2 of the K space in principle. there's no reason to take both plus K and minus K. But he did, which is, it's like signal averaging, but we're doing spherical K-space sampling. So we're just sampling all the K-space points within a sphere that goes out to the maximum K value in all directions, rather than sampling an entire cube. So you gain whatever that factor, I forget the factor of 2 reduction in the number of points by doing spherical K-space sampling.
Yeah. Wouldn't there be a polarization gradient moving, an anonymous attendee, wouldn't there be a polarization gradient moving away from the radicals in DNP enhanced MRI? How would the proton spin density and polarization be distinguished in your experiment?
I mean, that's true. There is polarizations diffusing away from the radicals at the concentrations we're working at. So like, 10 millimolar kind of concentrations, you don't develop very large polarization gradients, I think, in principle. But I think an interesting experiment to do, which is one of the things that I hope that we'll do, would be to do imaging on a very dilutely doped sample where at micromolar sort of concentrations of the dopants. And then you can maybe see the polarization diffusing out from an individual dopant, and then get a direct measurement of how much polarization you're getting from an individual dopant. So I think there's some interesting spin physics experiments that could be done there at very low dopant concentrations. And I hope that's something that we'll do in the near future.
And Mark Conradi, I guess the final question is, Bravo, is the bright spot in the center of the images of the spheres related to the optical diffraction effect?
Yeah, it's essentially, it's kind of, it's just these truncation wiggles that are adding up. Like you have these sort of truncation, K-space truncation wiggles coming from the surface into each sphere and propagating to the center of the sphere, where they add up constructively at particular wavelengths or particular resolutions. So it turns out at around 1.7 microns, you actually get the maximal constructive interference of these truncation wiggles in the center of the sphere, when the spheres are about 9.2 microns in diameter.
Yeah.
So it's kind of a sort of a diffraction effect. Yes.
Okay.
So thanks very much. Thanks for the questions.
Okay, there have been lots of questions. And Rob, thank you for the talk. And it's probably time we get on to the second presentation. And Kong, you want to do the introduction? Yeah.
Yeah, sure. All right. Thanks, Rob. I should be careful because there are 3 Roberts in this panelist. So Bob Griffin, Rob Schurko, and Rob Tycko. So I will introduce the second speaker. So we are delighted to be able to invite Rob Schurko to our ZOOMinar today. And he will be telling us about state-of-the-art techniques for acquiring and processing ultra-wide line NMR spectra. So Rob started as undergrad in University of Manitoba. Then he went on to do a PhD in Dalhousie University. After that, he did a postdoc with Claire Gray and Lucio. Following that, then he got a professorship position in University of Windsor, where he has started looking at a lot of ultra-wide light NMR spectra. And I think he's like one of the experts in this field who has looked at almost every NMR active elements in periodic table, if I'm not mistaken. And recently he has moved to Florida State University, and also serving as a director of the NMR and MRI user program, the National High Field Magnetic Field Laboratory in Florida. So the virtual floor is yours, Rob, please.
Great, and you can see my screen and pointer, okay?
Yeah, it looks good.
Excellent. Okay, well, first I'll thank Kong and Bob for giving me an opportunity to tell you a little bit about our work on ultra-wideline NMR. And so as mentioned, after 19 years up at Windsor, I moved down to FSU in 2019. And this was to, in part, take up this position at the Mag Lab. And despite the COVID pandemic, my group and I have had a great time working here, especially because of the great scientists and engineers and all of the gear that's on site. I'd like to do a quick advertisement for the Mag Lab, if that's permitted. We have 14 instruments, including our 36 Tesla series connected hybrid. So this does NMR at 1.5 gigahertz. We have an ultra-wide bore 900 megahertz MRI platform and a very unique 600 megahertz DNP NMR spectrometer. And we're always interested in having users, so please reach out because Magnet Time is free to all users anywhere in the world. So we'd love to have you either visit us or run your experiments remotely. As Kong mentioned, we work on solid-state NMR of nuclei across the periodic table, especially those that are unreceptive, and these constitute the majority of the periodic table. And of course, NMR spectroscopy of these sorts of unreceptive nuclei have numerous benefits for studies of molecular structure and dynamics across many disciplines in chemistry, biology, and physics. What is meant by an unreceptive nucleus? Well, we're all familiar with the ideas of low gamma, low natural abundance, maybe long relaxation times, or even the dilution of the nucleus you're interested in. But of course, in solids, large anisotropic interactions can also make a spectrum very difficult to acquire, rendering certain nuclei even more unreceptive. In our group, we focus on unreceptive nuclei a lot in ultra-wide-line NMR spectra, and these feature patterns that are about 250 kilohertz to several megahertz in breadth. So here's an example of an ultra-wide-line spectrum of a half-integer quadrupolar nucleus, copper 65. The central transition pattern here spans about 6.4 megahertz, and as such has inherently low signal-to-noise. But if you can extract the quadrupolar parameters from such a pattern, you can get very rich information, let's say in this case, on the copper environment in this molecule. So we actually have had a lot of success. We haven't done the entire periodic table, but we have done everything here in green. We could probably easily do the stuff in yellow. We just haven't had the right project come up. And some of our targets in the next few years include the ones here in the garnet color, which we hope to address using our methodologies and some of the great hardware here at MagLab. So today, I'll begin by giving you a bit of background on the frequency swept pulses and pulse sequences we use. And then I'd like to give you a snapshot of some new projects. And these are mainly conducted by Adam Altenhoff, a PhD student in my group who's just finishing his thesis, and he's online as well to help me with the hard questions today. And this includes a recently published paper on how to measure T1s from ultra-wide-line NMR spectra. And this is really nice work. But this leads to some recently submitted work on a new method for distinguishing overlapping ultra-wide-line patterns via their relaxation characteristics, and a new indirect detection method for static NMR using a solid-state NMR analog of CEST, which we recently published in JAX. And we've also been working on broadband CP processes and understanding them. I won't talk about this today. So let's start with a brief introduction to our frequency swept pulses and the associated sequences. Whereas rectangular pulses are widely used in all areas of NMR, they're most often of limited use for ultra-wide-line NMR spectra, providing only limited excitation bandwidths, even with very short pulse times and high powers. And you can see this from the spin echo and CPMG spectra here. And of course, block decays are generally not a good option for ultra-wide-line NMR. A possible solution to this conundrum is the use of frequency swept pulses, of which one of the most popular is the wideband uniform rate smooth truncation, or WURST pulse of Kupche and Freeman. And a particular interest is this phase profile that gives us a virtual linear frequency sweep. And these pulses, as a result, have much broader bandwidths than conventional rectangular pulses and are used for excitation, refocusing, decoupling, saturation, and also adiabatic inversion. And that will be a key here today. Luke Odell, a former postdoc in my group, implemented WURST pulses in a CPMG type sequence, which we cleverly named WURST CPMG. And this has been shown to be a very effective method for acquiring ultra-wide-line NMR spectra, providing both the benefits of bandwidth from the WURST pulses and the T2 enhancements from the CPMG sequence. But one does not always want to conduct ultra-wide-line NMR experiments using direct excitation, of course. And one of the most ubiquitous techniques we can use for polarization transfer is cross-polarization, or CP. However, conventional CP can be very limited in bandwidth. For instance, here one can see that the direct excitation spectrum for platinum yields almost the entire bandwidth, limited really only by the probe, whereas conventional CP-CPMG provides a relatively small bandwidth. So here's the stupid joke I make every time, and I can't help myself. You might say that this is a worst-case scenario, or maybe you wouldn't say this, but nonetheless, Chris Harris, a former postdoc in my group, worked on designing the broadband adiabatic inversion CP, or brain CP sequence, in a joint project with Lucio's group at Weitzman. And this sequence uses a standard pi/2 and contact time on the H channel, but uses a Wurst pulse for the dual purpose of polarization transfer and adiabatic inversion of the X-spin polarization along the longitudinal axes. And this is followed by a Wurst CPMG sequence that converts the adiabatically inverted X-spin polarization to observable signal, and then you have the usual echo train here. And a really nice thing about this is the sequence uses very low RF fields in comparison to conventional CP, and it puts a lot less stress on the probes, and therefore it's really well suited for low gamma nuclei. So let's consider what happens during the contact pulses, and in particular visualize what happens to S-spin polarization. We will do an I to S brain CP using a high to low frequency sweep here, and we'll just observe the behavior of a single isochromat in the middle. And what we'll do is we'll monitor the IX and the SZ polarization on this graph, and also watch what happens to the buildup of the S polarization. I'm going to start this now because it takes a while to get going. But basically what we're going to see is two matching conditions where we have depletion and then growth of the SZ polarization. And you can see that it's just about to start now, and you'll also see some inversion. So there is the first match, and there's some inversion, and then a second match, and then the magnetization gets locked along the negative Z axis in this case. The sequence is really robust and easy to set up, providing almost perfect storage of X-spin polarization along the longitudinal axes, since these Wurst pulses work really well for adiabatic inversion. And so this suggests to us that these would really be good for T1 measurements in particular cases. So probably one of the new projects here that I'll introduce is measuring T1s from ultra-wideband NMR spectra. And this is a basic idea, but it has big impacts on the projects that I'll discuss later. So everyone here is familiar with the standard IR sequence that's used to measure T1s. You use a pi pulse for inversion, a pi/2 for conversion to observable signal, and then you have your time tau, which is incremented to produce one of these decay curves. And we know that accurate knowledge of T1s is important not only for optimizing our experiments, but can also play a big role in studying molecular structure and dynamics. We've recently published this paper describing a variety of inversion recovery type sequences that can be used for ultra-wideline NMR, and they all involve CPMG enhancements. We have the CPMG T1. This uses rectangular pulses. And then we have brain CPT1 and Wurst CPMG. So these are for broadband cross-polarization and direct excitation. And all of these feature CPMG trains. And what we do in each case is plot the intensities of the spectra as a function of tau. So we'll focus a lot on this brain CPT variant. In particular, this is really good for spin-half nuclei with long T1s. Generally speaking, the T1s of the protons are going to be a lot less than the T1 of the X nuclei. And this is also, of course, very useful where T2-dependent signal enhancement is necessary. So in our first paper on this topic, we applied these methods and tested them to a variety of spin-half and quadruples. And in the interest of time today, the two examples I'm going to show you in a little bit of detail are the tin and platinum examples. So the first example is the tin 119 NMR of dibutyl tin oxide. It's not a true ultra-wideline NMR spectrum, but it's really good for setting up proton tin CP. As you see on the right, if we compare the brain CP and the CP CPMG, we get much nicer uniform excitation compared to the ideal pattern. And in addition, again, because of the much shorter T1s, this is really advantageous for measuring T1s for spin-half nuclei. You could see we'd have to wait a maximum of about 15 seconds between scans here, whereas it would be about 750 seconds for tin 119. So what we'll do first is look at the rectangular pulse version, CPMG T1. And what we do is we alternate the phases of the first proton excitation pulse by 180 degrees and collect two sets of data. And these result from storage of X-spin polarization along Z and minus Z. And then we take the difference of these data sets, which suppresses all of the non-CP signals from the S-spins, and this was proposed a long time ago by Torchia and Stejkal and Schaefer. And then we plot the integrated intensities of the patterns as a function of tau, and we can do both mono and bi-exponential fits to get T1 time constants. And here we get a mono exponential T1 on the order of about 140 seconds. However, it's clear that the pattern isn't uniformly excited, and we might be losing some information. So this is the brain CPT1 analog of what you just saw, and now you can see that we have nice uniform patterns, especially you can see from the side profiles here along the Z and minus Z directions, and the difference here. And here we measure a slightly lower T1, but it's still within the bounds of uncertainty, and this gives us confidence in our measurements. I note this data set took about 3 hours to acquire, I believe, whereas if you were to do it directly, it would take significantly longer, over 30 hours. Okay, so then we tested this on a true ultra-wideline NMR spectrum. This is platinum tetraamine dichloride monohydrate, and the powder pattern here is close to a megahertz in breadth, and shown at the top here is the ideal simulation, and then here's a brain CPT1 data set on the bottom, and the tau increments are projected along the right axis that you see here. So this is where things start to get pretty interesting. We move to a top-down view of the brain CPT1 data set. And the pattern is so broad that we have to acquire it in a stepwise fashion, 3 separate pieces at unique transmitter frequencies. And the projection of the data, the difference data set, shows this variation in the T1 decay time constants across the pattern, suggesting the possibility of T1 anisotropy. The longest T1 is found near about 128 kilohertz, right where you see the asterisk. And this is very close to the isotropic shift, or if you like, the magic angle isochromat. Of course, we were concerned when we were doing that this might be an artifact somehow of our experiment. So we did an analogous direct excite experiment, and we saw the exact same behavior. And these are plotted in magnitude mode, by the way. That's why they look like this. So this increased our confidence in our measurements. But just to triple check this, we measured T1 values independently for isochromats across the entire platinum 195 pattern. And so, for instance, at these frequency positions that you see marked here, we measured 3 distinct T1 values, and the shortest and the longest T1s come out as 1.2 and 4.4 seconds respectively. And this is a third check that we're confirming our hypothesis that there is a T1 anisotropy. And in fact, mono-exponential T1s are in agreement at each frequency and for each type of experiment, meaning we have found a net T1 anisotropy of about 3.2 seconds across the pattern. This is reminiscent of several older papers, including the observations of Pines, Gibby, and Waugh in the 1970s for proton-carbon CP experiments on enriched benzene at low temperature, where they found that the nuclei with the tensor orientations of theta equals 90 degrees or pi by 2 relax about 7 times faster than those with theta equals 0. And this was accomplished using a 180 tau 90 style inversion experiment. And there are numerous examples of these T1 anisotropies in the literature, including in the fluorine-19 and phosphorus-31 data of Maring, and even in some deuterium NMR spectrum from Bob Griffin's group. So this made us reconsider what we did with the TIN-119 and to ask the question, is it valid to take integrated intensities to get a measure of the average T1 value? And we found a T1 anisotropy for TIN-119 close to 50 seconds across the pattern. And the average T1 is in very good agreement with the T1 from the integrated intensities measured earlier. And again, the longest T1 is found in a similar position. So this makes us happy that we can, in fact, do those earlier measurements and pretty much accurately reflect the average T1. As I mentioned, we also did this for quadrupolar nuclei like chlorine, and this is the case of glycine HCl, and deuterium for alpha glycine. And things get really interesting here in terms of the multi-exponential relaxation and the ability to investigate potential contributing relaxation mechanisms, as well as the polarization transfers that influence the appearance of these spectra. I won't discuss this today, but the details you can find in this JChem Phys article from 2021 if you're interested. But a final note is a really neat advantage at MagLab is we have experts here in all sorts of areas of magnetic resonance. So Adam Altenhoff walked down the hall and talked to Krish Kundu, an EPR expert, and after some time they were able to implement our worst IR sequences to measure electron T1s, observe T1 anisotropy and tempo using EPR, which is also very exciting since all of this occurs on a much faster time scale than NMR, and these are basically brand new results. And you can see the top and the side views of the magnitude processed IR data sets here. So that's a really exciting pathway for us as well. Okay, so this project influences the last two that I'll show you here. And this is one of our newest projects. This was recently submitted to PCCP, and this is our 3D relaxation assisted separation method. So currently, when you're doing ultra-wideline NMR, when you have overlapping patterns, you have three options for resolving them. And one is luck, and the second is magic angle spinning, and the third is relaxation-assisted separation. So let's see what's meant by these three options. Now, I think luck is pretty obvious. Sometimes when you have overlapping patterns, if you have high signal to noise and you have very distinct EFG tensor parameters and high sample crystallinity helps, you can easily resolve overlapping patterns in these beautiful ultra-wideline NMR spectra. But what about MAS? Well, for ultra-wideline NMR patterns, MAS is really only effective if you could spin on the order of or higher than the breadth of the pattern. And for the majority of quadrupolar nuclei on the periodic table, MAS is ineffective in this sense due to the severe overlap between central transition, satellite transition patterns, and their sidebands. Even for this modestly wide chlorine spectrum, you have to spin upwards of 45 kilohertz to start resolving the sidebands. So practically, most quadrupoles you can only investigate under static conditions. What about RAS? Well, one thing you can do is if you have overlapping patterns from magnetically distinct sites, MAS isn't an option, you can easily differentiate things on the differences in T2. And this is accomplished with very simple CPMG experiments and spectral editing. Anybody could do this. It's very, very simple. But many times this isn't an option, especially in cases where the T2s are very close to one another. So what we worked on, we initially proposed a 2D relaxation-assisted method, basically separating patterns on the basis of both T1 and T2, inspired by the work of Bhattacharya and Friedman. And we collected a CPMG T2 data set. We arranged the echoes chronologically. We apply a fast Fourier transform. We do some Tycko fitting, some non-negative least square fitting to separate the patterns, and then some post-processing to clean things up. And you can see now the patterns are resolved on the basis of their T2 rates in this example. But there are two main problems here. The first is that this 2D RAS is very limited when the T2s are similar, not as much as the simple spectral editing, but there are limitations. And perhaps more importantly, secondly, if you have noisy spectra, the inverse Laplace transform or NNTF routines that you use become unreliable due to the ill-posed nature of the problem. And so the spectra in the green box here shows an idealized, a great case with high signal to noise and very different T2s. But you can see as the T2s approach one another and the signal to noise decreases, it's very difficult to separate these. So to address this, we can move from 2D to 3D RAS. And to address problem one, what we can do is encode our signal with T1 and T2 data instead of just one or the other. And T1, T2 correlation maps are well known in MRI and solution NMR, and so we figured we would try this for ultra-wideline NMR in solids. And to address problem two, instead of the standard inverse Laplace transform, we chose to stabilize the ILT with elastic net regularization. And this uses a linear combination of the two norms that you see here, which are weighted by the parameters alpha and lambda. And these are optimized to give you the best results. So in elastic net regularization, the L2 and L1 norm constraints serve to smooth the solution and also impose sparsity on the solution respectively, as shown by the best agreement here between the black pattern and the green pattern, which is the elastic net. So taking what we've learned from making our ultra-wideline measurements of T1 and getting RAS to work in 3D, can we separate overlapping ultra-wideline NMR patterns efficiently? And this will rely on stabilizing the ILT with our elastic net regularization, but Adam has also investigated denoising the relaxation data with PCA and further regularization and faster computation with truncated singular variable decomposition, leading to a really interesting sparse NNTF technique. You can download the software for this on our GitHub site if you're interested in checking it out. So for a synthetic data set with two overlapping patterns that are encoded with unique T1 and T2 values for each site, an NLS analysis featuring elastic net regularization and truncated SVD is used to obtain the 2D RAS plots you see here. This is for T1 and T2, and you can see very, very nice separation. And then here is the R1, R2 correlation map, or the 3D RAS, that helps to separate these patterns. And you can see their frequency representations on the right-hand side. So if you have data and it becomes noisy, this is still synthetic, by the way, 3D RAS will yield sort of a blurring of the signal and some sort of interference and overlap between the patterns. But if you do PCA regularization, and here we have optimized values of the alpha and lambda parameters, there's much better separation of the signal, and you get cleaner powder patterns extracted from the correlation map. So generally what we do for these experiments is, if we have, let's say, a mixture of 3:1 glycine and histidine HCl, 2 chlorine sites, we inquire CPMG data, which encodes the T2. And this is done for various values of T1, for tau, pardon me, in the T1 inversion experiments. And a data set at a given frequency point will now be encoded with both of these axes, and this is the 500th frequency bin that you see here. And these are required with some of the aforementioned ultra-wideline IR experiments. So if we separate these patterns on the basis of 2D RAS with T1, you can see that there's a lot of overlapped signal. And this can be cleaned up somewhat by elastic net regularization. It gives us pretty good results here, but the patterns are still distorted. However, if we do 3D RAS, we see that the patterns really separate out much more nicely, and we get really good isolation, and we get much nicer resulting undistorted powder patterns. And here's a really nice example from a chlorine NMR spectrum of a urea co-crystal. This has 3 magnetically distinct sites. And we can see that if we do worse CPMG with 200 co-added echoes and maybe just the first 10 co-echoes added, we can see that there's some subtle T2 variations in the pattern, but they're not terribly different from one another, it seems. But if we do our 3D RAS, the correlation map allows us to extract the 3 patterns, which we can simulate to extract the quadrupolar parameters. And in this case, this is our sparse routine with PCA denoising. So we think this 3D RAS method holds a lot of promise for many different spin half and quadrupolar nuclei that have overlapping wideline or ultra-wideline patterns. Finally, the last thing I'll tell you about quickly is this indirect detection technique, where we are detecting the ultra-wideline NMR spectrum of a dilute X nucleus, which is indirectly observed on the proton channel. And this is not an MAS experiment, but a static experiment, which borrows from the idea of CEST. Now, the CEST experiment, it relies upon chemically exchanging protons between dilute and abundant spin pools, and then the detection of the dilute signal via that of the much more abundant signal, which gradually depletes if the CEST mechanism is active. In this case, the proton NMR of salicylic acid, the water resonance dips in intensity when you apply saturation at about 14 ppm, and this indicates the carboxylic and hydroxy protons are undergoing exchange, and this can potentially lead to enormous signal enhancements. But of course, this relies upon chemically exchanging waters. So can an analogous solid-state NMR experiment be performed? Well, the problem is that we have no free bulk water really in solids, and second, no similar type of chemical exchange. However, in many inorganic and organic solids, we have many protons, and we do have spin diffusion. So we have sort of a similar scheme with a dilute spin pool and 2 sets of protons that will be very useful for making this work. So to visualize this experiment, we start off with our 3 spin pools. The X spin pool is coupled to a dilute pool of protons, which is dipolar coupled to the abundant pool, but the abundant pool is not coupled to X. We can do frequency selective saturation with CP, and the purpose here is to enhance the X polarization. And this is followed by repolarization of the coupled proton spin pool from the abundant proton spin pool. And then we repeat this step n times over many different transmitter frequencies on the X channel, and so this coupled pool is acting as a polarization valve. The answer to the pulse sequence design revealed itself in the form of adiabatic demagnetization in the rotating frame, ADRF, for the purpose of creating dipolar order, and concomitant adiabatic remagnetization. So a simple ADRF sequence can be used to create dipolar order, as you see here on the top right. And if we can create this dipolar order, then we might be able to perform CP with ARF, provided that the expectation value for our dipolar frequency is on the order of the B1 field that's being applied on the X channel. So the final sequence for our Prosper looks like this, where 2 experiments are run, a control experiment with no ADR FCP, and a Prosper experiment where the CP is activated. And if the CP is effective and an appropriate spin diffusion time is chosen, there's a gradual depletion of this bulk signal for each experiment run at different transmitter frequencies on the X channel, and the net proton signal will be the difference between the control and the polarization. So the idea here is that if we have a schematic of the X spectrum that we're interested in, this is the target, and this is our transmitter position, what we're going to see below is the signal detected via the abundant spin pool. So as we start moving the transmitter to different frequencies, the difference between the depolarized and the control spectra is plotted out as we move through the pattern, and we see that we have a manifold that takes on the shape of the target X spectrum. So here's an example for cis-platinum, platinum 195 NMR using Prosper, and the plot of the differences in intensities yields a pattern like you see here. And what we do is we extract the CSA pattern you see here, and it's very nicely comparable to the brain CP pattern. This is what we were talking about earlier. And these are very similar experimental times, about 1.6, 1.7 hours. But here's one more example, and this is the same cis-platin, but this is N14 NMR. And here we're able to use a much shorter mixing time for the production of the spectrum that you see here, really quite high intensity. And when we extract this spectrum, we see that we can conduct this in a much shorter amount of time than the 8.5 hours required for the direct excite of the nitrogen, and giving us a spectrum that highly resembles our idealized spectrum. So the optimization of this sequence is a bit involved. There's a lot of things that you have to measure, in particular the dipolar T1, and there's a lot of optimization to do, but we're working on simplifying this. And currently, in the paper, I should say, there's work on other quadrupolar nuclei like N14, sulfur 33, and oxygen 17, and some spin half nuclei. And we have ongoing projects here at MagLab and over at Weitzman to further advance this technique. So we are really excited about this unique CES-like experiment for static samples, and it's really showing some promise. And this just came out recently in JAX. So to conclude, I've shown you today a variety of brand new work on ultra-wideline NMR with a real focus on exploiting relaxation properties to enhance signal-to-noise and to enhance resolution. And we and other groups are continuing to push this frontier and strongly believe there's a lot to learn about spin dynamics, experimental optimization, and of course, ultimately, learning about the rich underlying chemistry of numerous materials and biological systems. Most, again, of what I showed you today is from Adam Altenhoff's PhD thesis, and a lot is from Mike Jarosevich as well, who is an undergrad and a master's student of mine up in Canada, who's currently wrapping up a PhD with Lucio, who's also involved here. So I'd like to thank them and Lucio and my colleagues at MagLab, and finally FSU MagLab, the state of Florida, and the NSF for generously supporting this research. And thank you again for coming today and attending my talk. We're happy to share our pulse sequences and software with you to help, and we'll help you get started. And also, please apply to the MagLab if you're interested in some NMR high field time here or DNP time. Thank you very much, and I'm happy to take questions now.
All right, thank you very much, Rob, for your very, very interesting talks, like showing us what you have been working on lately, especially with the R2D or 3D RAS, and also with showing us the CES-like sequence for the ultra-wide light NMR analogy. So I'll just like ask a simple question so that the participants have some time to type the questions in the Q&A. But before that, I just want to comment. I mean, Bob will definitely say this because he kept telling us when I was there. He said, Bob, you probably remember that you showed us the 1987 Bashaj paper where I think he talks about the T1 anisotropy. We also observed that in deuterium and alanine, right, Bob? Yeah. So yeah.
Yeah, I did mention that. I just I actually have a slide on it, and I have a slide on the 19F. Yeah, there's a lot of really beautiful classic examples of this in the literature.
Yeah, I remember because like that's what Bob asked me to simulate when I started there like 4 or 5 years ago. Okay, so Yeah, I'm just curious. I mean, since you talk about unreceptive nuclei, and then like since we do a lot of DMP here, and then it's also nice that you show that you're using like Woost plus for EPR, but do you also anticipate this being applied for DMP or doing something like DMP enhanced ultraviolet NMR? Is that something that?
Yeah, so we're actually that connects to Aaron's question that's going to be coming up. We're planning on doing DMP for both the sort of direct and broadband cross-polarization experiments that you see here. And I think we're quite a big fan of chlorine because of its application in pharmaceutical chemistry. And so, yeah, indeed, there's no reason these sequences shouldn't work under DMP conditions. And that's something we're going to be undertaking with Fred Montic-Vigier here at MagLab. But we're also, of course, interested in the indirect type sequences as well, especially for looking at correlations between the protons that are nearest to, let's say, chloride ions in organic solids. So both of them function quite well outside of DNP, but I think with DNP, there's really quite a bit of promise.
All right. So just go through the first question asked by Thomas Schmidt. Comment Tikhonov might represent some problems as it does not give an analytical solution. Recent advances in signal analysis have shown that point-by-point SVD through Srivastava and Merlin transform Matbiba might present an alternative to it.
Okay, well, I'll be quite honest. I am not familiar with the point-by-point Srivastava that much. I believe Adam has mentioned it to me before, and I think he's played around with it. And the Mellon transform. Adam is actually here. Do you want to respond to that, Adam?
Yeah, for sure. So I'm familiar with both those pieces of work. So the work by Madhur with the EPR and the SVD, inverse regularization problem. I think in that work, if it's the dipolar dephasing curves, he still does use Tikhonov regularization, if I'm not mistaken. But I do like that you mentioned the myelin transform. I just recently saw that paper. I think it was in JMR. And it does seem to actually give a much more stable solution, potentially with higher resolution actually, than anything from like Tikhonov or the standard sort of ILT. So I do like the idea of using myelin for sure. It's something I want like some junior grad students to play around with.
Thanks, Adam.
All right. So next question by Aaron Rossini. He doesn't share your pessimism about magic angle spinning. For the glycine histidine mixture, 2D proton chlorine inap or HMQC could easily resolve the patterns. Likewise, he has used proton platinum DHMQC to obtain high resolution platinum white light spectra.
Yeah, so Aaron, the case we showed there is a simple one, and those patterns are relatively narrow, and I agree 100% that you could easily do that with an indirect experiment. So that mixture of those two samples is basically just a test case. But let's remember that most wide-line and ultra-wide-line patterns aren't quite like that. And in specific, my pessimism with MAS is not in regard to spin half nuclei like platinum, but if we're doing something like cobalt or rhenium or copper or something like that, where in some cases the patterns are just ridiculously wide, the central transition patterns, and maybe in cases like cobalt, there's really severe overlap of the central and satellite transitions. The MAS is basically a mess. So I do not disparage MAS at all. It's clearly one of the most valuable tools that we have in NMR. It's just that there are many situations where it's not a possibility. And I should mention for everyone here, if they're not familiar, Aaron has done really brilliant work on indirect detection of ultra-wideband NMR, and we are big fans of that, and we are using his sequences as well. So thanks for that, Aaron. That's a good point.
All right. Next question by Brian Lucier. The work on T1 anisotropy in broad powder spectrum pattern is very interesting. To pick up on an old thread, have you done any exploration into possible T2 anisotropy in broad powder patterns?
Yeah, we have. A lot of it was done in the past, and we've noticed it in N14 N14 CPMG spectra, but there's sort of a weird problem here that, there's a question about what is the natural T2 and what is the effective T2. And so for instance, if you acquire a CPMG echo train and you have a lot of protons in your sample, you normally have to apply decoupling to reduce the contributions of the protons to basically relaxation and dephasing effects on the echo train. And so in some cases, like in some samples we've looked at with N14, there seem to be T2 anisotropies in some conditions, and then if you turn up the decoupling, the T2 anisotropies disappear. So and the reverse situation actually happens as well. So it really becomes a question of, what is meant by the natural T2. And of course, even if you change temperatures, you can change T2 anisotropies. So the T1, I guess, as a contrast, is a lot simpler to study because there's nothing much we can do to alter it except change the temperature. There's not really an effective T1, if you will. So yeah, it's a very interesting question and something I'm definitely interested in. And perhaps some of this will elicit more of itself with Adams routines that are being used to not only make these sorts of measurements, but separate the patterns.
Okay.
Thanks for the question, Brian.
Yeah, another question from Aaron Rossini. Can you use a broadband CP pulse in Prosper sequence to maximize the signal dephasing on the proton side? For example, replacing that with ARF or ADRF with boost pulse?
Yeah, that's a really good question and something I think probably Mike Jarosevich has thought about for a long time. This was something we had sort of planned to do, but at this point, it was just the sort of sheer difficulty in getting the right set of conditions to make the Prosper work at all. For like sort of narrow, for small transmitter steps. That's sort of been the problem. On our end right now, what we're trying to do is measure the dipolar T1s for. I shouldn't say the dipolar. The T1s associated with dipolar order, in order to find some samples that would let us explore this possibility of doing something more broadbanded. And from what I understand on Lucio's end, they're continuing to look at some narrower patterns from sulfur 33 and N14 NMR spectra. So I'm not sure that they're working on that aspect of it yet. But for now, I think our main objective is to find a set of conditions that reliably gives us the Prosper effect. And once we do, then we could start exploring something more broadband in this sense, the more broadband ADR FCP.
All right. Thank you, Aaron and Rob, for questions and answers. Bob, you have any questions?
No, I think we've covered a lot of territory this morning, really very nicely. Both beautiful talks, right? So we should thank both speakers again for really wonderful presentations. Rob and Robert, okay. Yeah, and so we'll be back here again next week. We've been going on for about 2 hours already today. We'll be back here in 2 weeks, okay? With, let's see, who's going to be talking in 2 weeks? You want to announce it now?
Yeah, sure. In 2 weeks, we will be hosting Kazuki Takeda from Japan. So he will be staying up late for us. So we should take opportunity of that. And the second speaker will be Claudio Lucinat.
Yeah.
Yeah.
So again, thanks to everybody, okay? And we will see you in 2 weeks' time, all right? Bye.
Bye.
Bye-bye.